Hi, we've explored how univariate analysis allows us to understand individual variables. Now, let's expand our view with bivariate analysis, which involves examining two variables at a time to understand the relationships and interactions between them. This type of analysis is key for identifying potential cause and effect relationships. In bivariate analysis, we often ask how one variable may affect or be associated with another. For continuous variables, we might use correlation analysis to quantify the strength and direction of the relationship. When dealing with categorical variables, cross-tabulation becomes a useful method to observe the relationships in a tabular form. Now, moving beyond bivariate analysis, we come to multivariate analysis, where we delve into more complex territory, examining more than two variables simultaneously. This method helps us to unravel the intricate web of relationships and dynamics between multiple variables. In multivariate analysis, our focus shifts to understanding how several variables may interrelate and how they might collectively impact a single outcome or multiple outcomes. This analysis is particularly valuable in fields such as market research, health sciences, and social sciences. In these domains, it's rare for outcomes to be influenced by a single factor. Instead, multiple factors often interact in complex ways to influence results. Understanding these relationships can inform predictive models, guide decision-making, and lead to more effective interventions or strategies based on how different variables influence each other. Now let's understand how to determine relationship between two variables. Understanding the relationships between variables is a key aspect of both bivariate and multivariate analysis. Let's explore how these relationships can be visualized and interpreted across different types of variables. 1. Continuous versus continuous. When we analyze two continuous variables, such as market value and square feet of properties, we often use a scatter plot to visualize their relationship. Each point on the scatter plot represents an observation with its respective values for the two variables. By observing the pattern of points, we can infer the nature of their relationship. For instance, if points tend to rise together, this suggests a positive correlation, indicating that as one variable increases, the other tends to increase as well. 2. Continuous versus category. Comparing a continuous variable with a categorical one, such as price by state, requires a different approach. A box plot is a suitable tool here, as it displays the distribution of the continuous variable, price, and for each category, state. The median, quartiles, and potential outliers within each state can be compared side by side, offering insights into the differences in price distributions across different states. 3. Category versus category. For two categorical variables, cross-tabulation is an effective method to examine the relationship. It creates a table that displays the frequency of each category of one variable relative to the categories of the other variable. The cross-tabulation of city versus property type helps us see how many of each type of property is found in each city. This method is excellent for revealing patterns and potential relationships between categorical variables. Each of these methods, scatter plots, box plots, and cross-tabulation, provides unique insights depending on the type of variables being analyzed. Understanding these relationships is crucial for developing hypotheses, informing statistical tests, and making data-driven decisions. Now moving to multivariate analysis. When we extend our analysis to multiple variables, we enter the domain of multivariate analysis. This allows us to see how various factors interact with each other and affect the outcome. The box plot presented here is an excellent example, depicting the relationship between the price of properties, the number of rooms, and their location. Each box represents the price distribution for properties with a certain number of rooms in different locations: urban, suburban, and rural. The central line in each box indicates the median price, the edges of the box show the first and third quartiles, and the whiskers extend to the furthest points within a reasonable range, typically 1.5 times the interquartile range. Points outside of this are considered outliers and are marked with diamonds. By observing the boxes, we can compare the central tendency and variability of property prices across different numbers of rooms and locations. For instance, we might see that urban properties with 3 rooms have a higher median price than rural and suburban ones, indicating a possible premium on urban locations. Furthermore, the range of prices, as indicated by the whiskers, can tell us about the variability within each category. A larger range suggests greater diversity in property prices. Such visualizations help us to quickly identify patterns and possible correlations. For example, if we see that larger houses tend to have higher prices and this trend is consistent across different locations, we might infer a positive correlation between the size of a property, number of rooms, and its price, irrespective of the location. Multivariate analysis is powerful because it gives context to data, revealing complex structures and relationships that are not evident when variables are analyzed in isolation. It is particularly useful in fields where interactions between variables are key, such as real estate economics, demographic studies, and market segmentation. Now let's move to an important method used to determine relationship between variables, which is correlation. Correlation is a statistical measure that describes the strength and direction of a linear relationship between 2 variables. It is quantified by the correlation coefficient, usually represented by the letter R. The value of R ranges from 1 to +1, where a value of +1 indicates a perfect positive correlation, meaning that as one variable increases, the other also increases. A value of 0 suggests there is no linear relationship between the variables. A value of 1 indicates a perfect negative correlation, meaning that as one variable increases, the other decreases. Interpreting the value of R, values closer to 1, or 1 signify a strong relationship. If R is near 1, it shows a strong positive linear relationship, and if R is close to 1, it indicates a strong negative linear relationship. Values near 0 imply a weak or non-existent linear relationship between the variables. The formula for AR is the sum of the product of the standardized values of x and y, divided by the product of the standard deviations of x and y times the number of pairs minus 1. Sounds complex? Let's break it down with an example. Consider this dataset with variables x and y. To find the correlation, we first calculate the mean of x and y, then determine the deviation of each observation from their respective means. Next, we multiply these deviations for each pair of observations. This gives us a set of products that we sum together, which will form the numerator of our correlation formula. Summing up our products, we get a total of -10 for our numerator. For the denominator, we separately sum the squared deviations for x and y. Then we take the square root of each sum and multiply them together. After calculating, we find that both sums of squares are 10, and their square roots are both approximately 3.16. Multiplying these together gives us a denominator of 10. Finally, we divide our numerator by our denominator. -10 divided by 10 gives us a correlation coefficient of -1. This result of -1 indicates a perfect negative linear relationship. In practical terms, for every unit increase in x, there is an equal unit decrease in y. Understanding the Pearson correlation coefficient is key to exploring relationships in data.